Hi, everyone. Thank you for joining today's webinar. My name is Sakshi Sethi. I manage OIDA membership here at OSA. I'm really excited to introduce today's presentation. It's sponsored by Optotest and 3M. But before we get started, I just want to take a minute to review a couple of housekeeping items. So you'll see a few quick points up on the screen. So if you need any assistance on today's webinar, just use the chat icon at the bottom of your screen. You can send me a message there privately. I'd be happy to assist you with any issues that you might be having or any questions or comments you may have. During the webinar, we really encourage you to ask our speakers some questions. So at the bottom of your screen, you'll see a second icon. It says Q&A. You'll just type your question there. You'll hit submit. You have the option of submitting questions anonymously if you'd like. All questions will be answered at the end of today's presentations. Our speakers have allocated some time for discussion and Q&A. So we encourage you as they come to you, please type them and submit them. And then a final reminder, the webinar today is being recorded. So a video will be posted on our website in about a couple of days. It will be made available to everyone. So if you can't stay for the entire webinar today, you want to rewatch it, you want to forward it onto a colleague, you're more than welcome to do so. In just a couple minutes, I'll drop a line in the chat box for the URL where you'll be able to find that in just another day or two. And I think that's everything I have for housekeeping. So I'd like to turn things over to Chris with Optotest, and he will get us started. Thanks.
Can you guys see my screen?
Looks good.
All right. Thank you for attending this webinar focused on insertion loss and return loss testing of complex cable assemblies. I'm Christopher Heisler with Optotest Corporation. I've been in the fiber optics industry for roughly 15 years. I sit on various TIA committees as well as IEC working groups to help develop fiber optic test procedures. Optotest has chosen to partner with 3M to help showcase their new EVO connector. Paul LeBlanc will be presenting on their behalf. Paul, would you like to introduce yourself?
Sure, Chris. Thank you. Again, my name is Paul LeBlanc, and I'm with 3M Company. I've been fortunate to develop all sorts of new products with 3M over the years, ranging from broadband copper to wireless and fiber optics. And I'm excited today to briefly review our new EVO connectivity.
All right, thank you, Paul. Now, a quick overview of Optotest. Optotest has been designing fiber optic test equipment for over 15 years. In that time span, we've partnered with industry innovators to develop adapters and solutions for the newest optical connectors and components. We are an ISO 9001 compliant company, and our products are designed and manufactured in the USA. In this webinar, we're going to be looking at equipment options for insertion loss and return loss testing of fiber optic assemblies. We'll look at methods to test hybrid patch cords, new unibody duplex connectors such as the CS, SN, and MDC. We'll look at loopback assemblies and how to test duplex and MPO type loopbacks. We'll also look at testing setups for shuffle assemblies, as well as some expanded beam options, and focus on the EVO connector. However, unfortunately, we'll not be able to cover ruggedized assemblies. Due to time constraints, we would not be able to give this topic proper attention. Please stay tuned for an upcoming webinar on this topic from Optotest. Now looking at some equipment selection for insertion loss and return loss meters, there's three main different configurations. There's a simplex system. Simplex systems are good for testing simplex assemblies, hybrid assemblies, as well as multiple simplex assemblies. So if you have a trunk assembly with multiple simplex cables inside of it. There's also multi-channel options, which have an integrated internal switch. These are good for testing multi-fiber connectors, as well as multiple simplex connectors at one time. One can also take a simplex system and expand it with an external switch to create a multi-channel system if needed. Now looking at the optical power meter side of things, a multi-channel power meter is good for testing DUTs with multiple connector types. And also when coupled with an optical source, a multi-channel power meter can help discern polarity on multi-fiber assemblies. There's also integrating sphere and large area detector options. These allow for large wide aperture connectors, such as MPOs or unibody duplex assemblies. However, these detectors cannot discern polarity, as the detector cannot tell which port the light is coming out of. Now, looking at testing hybrid cables. Hybrid cables are cables that have dissimilar connectors on each side. So, for example, FC to ST or FC-SC assemblies. These types of assemblies have similar connector types with the same ferrule size and the same polish angle. So these have 2.5 millimeter ferrules, and they have flat polished angle, a flat polished end. So in this case, you can use hybrid mating adapters to accommodate the testing. Here's an FC to SC mating adapter, an FC to ST mating adapter. And in these, you can also use universal OPM adapters to allow for connector interchangeability. Two of the more common universal OPM adapters are the 1.25 millimeter adapter for LC and MU adapters or connectors. And this is the 2.5 millimeter universal adapter. So a quick example on how to test one of these hybrid cables with an FCPC or to SCPC cable. In this case, we're going to use one reference cord, which will have an FCPC reference connector. The system setup is going to be a simplex system with one universal 2.5 millimeter OPM adapter. To reference, we're going to connect our reference connector, which in this case is an FCPC connector, up to the optical power meter, and we'll reference insertion loss and return loss. Now, to test the FC side of our FC to SC hybrid cable, we're going to use an FC to FC mating adapter to connect the FC side of the DUT to the FC reference connector. And then we're going to connect up the SC end to our universal 2.5 millimeter OPM adapter. And this will measure insertion loss and return loss on this connection here. Next, to test the SC side, we need to mate the SC connector of our DUT to the FC connector of our reference cord. To do this, we need to use an FC to SC mating adapter. So once we mate those up, we connect up the FC side to the universal 2.5 millimeter adapter, and then we can test insertion loss and return loss on this connection here. Now, many hybrid cables have ends that are unmateable to each other. So for example, some assemblies may have a flat connector on one side and an angled connector on the other side. In this case, you can't use the same reference cord to test both those connectors. One of the most common hybrid cables is an SC to LC assembly. So here you see that we have an LC assembly here. Move this. Here we have an LC connector here, which has a 1.25 millimeter ferrule. And here's an SC connector, which has a 2.5 millimeter ferrule. Now, one might think that you can use a mating adapter to couple those two together. However, these SC to LC mating adapters, the split sleeve has different diameters, and it can't maintain the proper concentricity to yield consistent results. So these types of mating adapters produce inconsistent results, and they shouldn't be used for test and measurement, especially for single mode assemblies. So for efficient measurement of this type of a DUT, we want to use a 2-channel system. We're going to have 2 switch channels, and we're going to have 2 optical power meter ports. On the optical power meter ports, we're going to use a universal 2.5 millimeter adapter and a universal 1.25 millimeter adapter. We're also going to use 2 reference connector or 2 reference cords, one with an SC connector and one with an LC connector. Sorry, one with an LC connector. Now to reference, we're going to connect up our SC reference connector to the universal 2.5 millimeter OPM adapter, and then we're going to connect up the LC to the universal 1.25 millimeter adapter. And then we're going to reference insertion loss and return loss after doing that. To test the DUT, first we need to swap the OPM adapter. So what we're going to do is we're going to take the 2.5 millimeter adapter that was on top, we're going to put it on the bottom. We're going to take the 1.25 millimeter adapter that was on the bottom, and we're going to place it on the top power meter port. Now to test the SC side of our DUT, we're going to connect up the SC connector to our SC reference connector via an SC to SC mating adapter. Then we're going to connect the LC connector to our 1.25 millimeter OPM adapter here, and we're going to measure insertion loss and return loss on the SC side here. Now to measure the LC side, we're going to connect up the LC connector to our LC reference cord. And then we're going to connect up the SC side to our universal 2.5 millimeter adapter. And that will measure insertion loss and return loss on this connection here. Now, a quick overview on testing hybrid cables. You want to use universal OPM adapters. This allows you to test multiple connector types without having to swap out the OPM adapters. You want to use hybrid mating adapters for connectors that have the same ferrule size, so SCs, FCs, STs, or between an LC and an MU type of a connector. For DUTs that have unmatable ends, such as an SC to LC or an assembly that has a flat to angle, you want to use a 2-channel system with 2 reference cords, one for each side of the DUT. And also do not use hybrid mating adapters for connectors that have unlike ferrule sizes, so 1.25 millimeter to 2.5 millimeter conversions. So now looking at mini duplex unibody connectors. Over the past 2 years, various duplex unibody connectors have been released. There's the MDC connector by US Connect, and there's also the CS and the SN connector by Senko. These types of connectors are similar to a duplex LC, except there are no simplex versions of them, so one must test both ports at the same time. A lot of times people will test duplex LCs using a simplex LC reference cord. However, these types of connectors do not have simplex versions, so you need to test both at the same time. Also, due to the wide pitch of the ferrules, a standard simplex detector cannot detect the light from both ferrules. So you typically need to break out the signal to 2 different detectors or use a large area detector or an integrating sphere. So there's various different methods to test these types of connectors. The first method that we are going to show here, you're going to use a 2-port IL-RL test set. You're going to use a large area detector or an integrating sphere such as shown here, and a dedicated OPM adapter for the specific connector type. So here we're going to be testing a MDC connector. We're going to use a MDC OPM adapter for the integrating sphere. Now to reference, we're going to connect up our reference cord directly to the integrating sphere, and we're going to reference insertion loss and return loss in this setup. To measure our DUT, we're going to connect the DUT in between the reference cord and the integrating sphere, and then we're going to measure insertion loss and return loss on side A here. So that'll be for 2 ports. We're going to measure IL and RL on side A. To test side B, we're going to flip the cable, and we're going to measure insertion loss and return loss on side B for both ports. Now this measures the IL and RL for all 4 ports. However, it doesn't validate polarity on the cable, and that's because the power meter can't tell which port the light is coming out of. So method 2 employs using a large core breakout receive cable. So what's the purpose of this large core breakout cable? Basically, it provides a 0 loss connection to route the light to the OPM. Effectively, it's an extension of the optical power meter. So this breaks out the simplex OPMs as well so that you can discern polarity. The large core fiber must be significantly larger than the test fiber and have a larger NA than the test fiber. So if you're testing 50 micron DUTs, using a 62.5 micron large core receive cable is good enough. And then for single mode assemblies, you can use 50 micron or 62.5 micron. And so given that there are no massive issues with the connection, all of the light from the smaller fiber, so in this case a 50 micron fiber, will couple completely into the large core fiber and route to the OPM. So this would be a 62.5. You see that all the light from this fiber couples into this with 0 loss. So the method 2 for testing these types of assemblies, to perform a return loss reference, we're going to have our launch cord connected up to our system. We're going to leave the end of the launch cord open to air. So we're going to reference return loss with this setup for both ports. And then to reference insertion loss, we're going to connect up the launch cord to the receive cord. And again, these are a 0 loss mating here. So we're going to reference insertion loss for channel 1 and channel 2. In this case, channel 1 will route to OPM 1 and channel 2 will route to OPM channel 2. Now, to test the DUT, we're going to connect the DUT in between our launch cord and the receive cord. We're going to test insertion loss and return loss at side A. Again, this is a 0 loss connection here, so there's no contribution from side B in the measurement for IL on A. So to test side B, we're going to flip the cable. Oh, sorry. We're going to flip the cable, test insertion loss and return loss on side B here. In this case, this also verifies polarity. So when we're using a receive breakout, light will be present on a single channel and will be expected on a single OPM as well. This will verify the polarity. If fibers are crossed in our DUT, then we'll receive dark measurements on our power meters. And this would indicate a fail of polarity. So when comparing the two methods, the large core receive cable versus a dedicated non-contact OPM adapter, the receive cable, the pros are that it's a zero loss connection, which removes the contribution to the loss measurement. It allows for insertion loss and polarity to be measured simultaneously. The cons is that it's a fiber-to-fiber mating, which promotes damage to the connector. So this requires inspection twice, which is time-consuming. So because on the receive side, this is a fiber-to-fiber mating, you should inspect that connection prior to making that connection, whereas in the previous method with the dedicated non-contact OPM adapter, you don't have to worry about inspecting that end that connects into the OPM. Another con is that the loss may still occur if dirt is present on the receive cord connection. Now looking at a dedicated non-contact OPM adapter, the pros are that there's less inspection. You don't have to worry when you make that OPM connection, so there's no need to inspect it, and also reduces the likelihood of damage. The cons is that it does not verify polarity, so if you want to verify polarity on these assemblies, you need to either do that before or after the insertion loss and return loss measurement. Now moving on and looking at fiber optic loopback components. Loopback assemblies route fiber optic ports of a connector to fiber optic ports within the same connector. So here we have a duplex LC loopback. We're going to, you'll see that this port just directly routes around to the opposite port. Now here's an MPO loopback, and on this, ports on one side of the connector will route to ports on the other side of the connector. So typically these assemblies are used to complete a return path from the transmit to receive side of a transceiver. So these would be for testing transceivers. And also they may have induced attenuation for stress testing transceivers by degrading the signal power and simulating the maximum loss budget of a system. Now, an example tests on a duplex loopback. In this case, we're going to be testing a duplex LC loopback. So we're going to treat this like a simplex patch cord. The loopback has two ports, but only one link. So when we select our reference cord, we want to select a reference cord that has a connector that is the same as the DUT that we're going to be testing. So we're testing an LC loopback, which means we want to use an LC reference connector. So to reference, we're going to connect up to our power meter. We're going to reference insertion loss and return loss here. To perform the measurement, we're going to take our reference cord, connect it to the input of our loopback, and then we're going to take a receive cord and connect that to the output of our loopback. In this case, when we measure insertion loss, return loss, the insertion loss measurement is going to be a total link loss. So we're going to get the combination of the input connection and a combination of the output connection. And for return loss, because this assembly is a short assembly, we're going to get a combination of the two connectors together. So we're going to get a total return loss of connection 1 and connection 2 inside this loopback. Now looking at MPO loopback assemblies, these are typically housed in one monolithic connector. So in this case, we have a 4-fiber loopback. We have 4 going in and 4 coming out. Here's a top view of it. We have the 4 inputs that route back through to the 4 outputs. There are multi-row loopback MPOs. These may have the transmit and receive split between the rows. So the top row will transmit and the bottom row will receive. And because these are in a monolithic, one monolithic connector, sometimes the equipment and cabling requires unique configuration. So now looking at the equipment required, we do need an equipment cord, and this equipment cord should be the same channel count as the link count. So if we're testing a 4-fiber MPO fan out or MPO loopback, we're going to need a 4-fiber MPO fan out for our equipment cord. Now on this connector, we're only populating 4 fibers, but on the connector here, when we make this connector, we actually want to populate all 12 fibers. And the reason for that is if you leave fiber holes empty, dirt and debris will build up in there, and that dirt and debris can potentially move around on the ferrule and damage the actual fibers. So we want to populate that entire connector with 12 fibers. Now, this is another portion of the optical assembly we're going to use for testing. This could be called a launch/return cord. It's somewhat of a complicated fan out. We have 2 MTPs that fan into 1 MTP. We populate fibers 1 through 4 on this MTP, and those route to fibers 1 through 4 on this MTP here. And then we're going to have the return path. We're going to populate these 4 fibers, and then on the return MPO connector, we're going to have these 4 fibers populated. So we're going to launch through here, and then it's going to go through the DUT, and then we're going to receive, or we're going to catch the return light on this connector here. So for the equipment setup, we need to use a system that's has at least as many channels as the DUT that we're going to be testing. So we're testing a 4-fiber MPO here. We need a 4-channel system. So we're going to connect up our 4-fiber fan-out equipment cord to the instrument. Then we're going to connect the end of the equipment cord into the launch side of our launch/return cable. We also need to have a large area detector or a integrating sphere here, and that's basically just to measure, be able to measure all of the light coming out of this MPO ferrule here. So to reference, we're going to connect up our MPO reference connector to the large area detector. We're going to reference insertion loss and return loss at this location here. Then to measure the DUT, we'll connect up our DUT to our reference connector here. And we're going to connect the optical power meter to our return leg on the fan out here. So the light's going to come through, route back around, and we're going to measure power here. And again, this measurement is a total link loss, so we're going to get the insertion loss of the mating at this connection and the insertion loss of the mating at this connection. So you get a combination of both. Also, for return loss, this is a short assembly, so we're going to get a combination of both connections as well. We'll get a total RL of this assembly here. Now, looking at shuffle testing, optical shuffles are fiber optic assemblies that route many inputs to many outputs. Testing these can be time consuming and ultimately confusing. Many times a D-shuffle assembly can be used to reorganize the links to a manageable testing scenario. So here's an example shuffle. We have 8 MPO connectors coming in. They route through, fibers get shuffled here, and then they route here to 12 MPOs coming out. So it looks like maybe this is a 8 12-fiber MPOs that go to 12 8-fiber MPOs here. So looking at an example shuffle here, we have 6 MPO connectors on the input and 6 MPO connectors on the output. Each fiber of each input connector routes to the corresponding port of the output connector. So here we have, this is connector 1. All of the fibers from connector 1 will route to port 1 of each of these connectors. So fiber 1 here routes to port 1 here. Fiber 2 routes to port 1. Fiber 3 routes to port 1. Fiber 4 routes to port 1, etc. Then for this connector, fiber 1 will route to port 2. Fiber 2 will route to port 2, fiber 3 to port 2, etc. So a straightforward test method suggests that we're testing one link at a time. So if we have our reference connector here and our receive cord here, when we want to test link 1, we're going to test link 1 here. We're going to test link 2, so we have to iterate to the next port. Link 3, iterate to the next connector, so we're at 5. 6, then we want to test 7. We're testing link 7, link 8, 9, 10, 11, and 12. So you see, we needed to connect multiple times to these output connectors to be able to test this entire assembly. So we're doing multiple connects and disconnects. Not only is this time consuming, but you're potentially going to damage your connectors the more times that you connect and disconnect to them. The likelihood that you damage them is very good. So there's got to be an easier way here. So for a simpler test method, use a D-shuffle assembly. This assembly inverses the effects of the shuffle and greatly simplifies the test. So to reference, we're going to use a large area detector, and we're going to connect up our reference connector to the large area detector. We're going to reference insertion loss and return loss for all ports on this connector. So to do the testing, we're going to connect up a deshuffle system to our shuffle. And what this deshuffle system does is it's basically going to route the fibers from this connector back to the fibers of this connector here. And it greatly simplifies the testing and reduces the amount of time that we're going to connect up to our DUT. So for example, here we go. We're going to test connector 1. So we're going to test here link 1. And you'll see that link 2 shuffles back to the first connector. Link 3 shuffles back to the first connector. Link 4, link 5, link 6. And we're going to go to link 7, 8, 9, 10, 11, and 12. Then we're going to do 13 through 18, then 19 through 24, 25 through 30, and then 31 through 36. So you see that we only connected up one time to these output ports and only one time to the input ports. So that reduces the likelihood that we're going to be damaging our connectors on the DUT. Also, a lot of times these shuffles, the deshuffle is actually the same mapping as the actual shuffle that we're testing. So if you want to deshuffle this system, you just take the same shuffle and connect it to the output of it. Quick overview of shuffle testing. There is no one-size-fits-all approach for a shuffle. The testing method depends on the connectors used, the polarity, etc. A deshuffle assembly greatly reduces the amount of connects and disconnects to the DUT. So this simplifies the testing process greatly, and it also reduces the likelihood that you're going to damage your DUT during the testing process. A deshuffle of the same core size will produce a link loss result. So if you use the same core size for your deshuffle as the DUT, you're going to get both connections included in the measurement. A deshuffle with a large core fiber will produce a one-sided loss result. So if you use a deshuffle that has a larger core fiber than your DUT, that large core fiber produces a zero loss connection. You only get a single-sided result. Now moving on and looking at expanded beam connectors. There are multiple expanded beam options available. There's the EVO connector from 3M, the MXC, Prism LT, and Prism MT from US Connect, and there are various ruggedized military grade options. So what's the purpose of these expanded beam connectors? Well, there's a drive to build connectors that are easily installed and can be considered somewhat foolproof. For these to be foolproof, they need to be dust resistant and resilient. So in this graphic to the right here, you see that we have a 3-micron speck of dust on a single mode fiber. So this is a 9-micron single mode fiber. This 3-micron speck of dust, has some coverage over this fiber. It impedes the light coming out of the fiber, and it gives you roughly an 11% coverage over that fiber, which produces about a 0.5 dB insertion loss. Now, if we expand this 9-micron beam to an 80-micron beam, you see that this 3-micron speck of dust is much smaller percentage-wise to this 80-micron expanded beam. So this 3-micron has a coverage of about 0.14%, which gives about 0.01 dB of loss. So as we expand the beam, the effect of the particle is less on the throughput of that connector. Also, these connectors are non-contact, so inspection and cleaning is less necessary due to the lower likelihood of damage due to mating. So on typical connectors, you're taking two fibers and you're basically butting them up against each other. If one of those fibers has dirt or contamination on it, you're potentially going to jam that dirt and contamination on the other connector and damage both connectors. In this case, with non-contact, you're not going to run into that issue. Many of these connectors don't have standard OPM adapters available. So due to large spot size, there might be an interference with the standard OPM adapter apertures. So because of this, we need to devise methods to couple light into the OPM and measure it accurately. Also, these are non-contact connectors, and sometimes the return loss is a function of one termination in the mating rather than a combination of both. So for standard physical contact connectors, it is assumed that the return loss of a connection is independent of the direction. So For example, we have two fibers butted up against each other. These fibers have the same refractive index. If we measure return loss from the left side, we're going to get a return loss value. Then when we measure from the right side, we're going to get a return loss value. And because these have the same refractive index or close, the return loss from one side and from the other side is going to be roughly the same. Now, if you look at an assembly that might not have a proper physical contact, so for example, this might be an angled to a flat mating. From the angled side, you're going to get very low reflection because an angle to air has a low return loss. Now, from the right side, you're going to get a large reflection because a flat to air has a very large reflection. So you see that the directionality of the return loss does matter when you don't have two fibers mated to each other. So expanding on that and looking at these non-contact connectors, return loss is largely governed by the source side connector. So if we're measuring return loss from the left side here, light's going to come in, it's going to expand out, and it's going to hit the receive side optics here. When it interacts with those optics, it's actually going to reflect away from the source side connector. This light will not couple back into this optical assembly. Well, so a lot of the return loss that we see from this side is actually due from this optical assembly here. Now, if we come in from the other side, again, the light expands out, and when it reflects on this assembly here, it's going to reflect away from this optical assembly and won't couple back into the fiber. The return loss seen from this side is likely due to, and largely due to, this optical assembly here. So when we're testing these expanded beam assemblies, where do we measure return loss? So here we have a typical setup. You have a reference core here. You have your DUT, which is connectors B to connector C. Then we have a receive cord, which would be connector D. Now, if we want to measure return loss from the left side, we're going to shine light in from the left. We'll have this connection here, which will create some return loss. However, that return loss is largely due to the A side connector, which is the reference connector and not part of the DUT. So as light passes through, we're going to get a return loss component from connector C here, which is part of the DUT. And then light will continue through to the receive cable. So typically when you measure return loss on a connection, you measure it on the front side of a DUT. However, the return loss measured at this front side is largely due to connector A. If we want to characterize the DUT, you want to actually measure at connector C because that's where we get a component associated with the DUT. Now, if we wanted to measure return loss associated with B, we would need to flip the cable. So if we flip B here, as we shine light from the left to right, we'll get our RL component for B. So we'd want to measure on the opposite side of our DUT than we typically do. Now, looking at these EBO assemblies, these are 90-degree non-contact assemblies. The ferrule is enclosed and shrouded inside the connector, and there's no easy way to couple the connector into an OPM and accurately capture the light. So if we look at a standard MPO connector here, light comes directly out of the connector, and you can put a detector right in front of it and directly measure the light. However, for these EBO connectors, these are a 90-degree assembly, so the light comes out from the ferrule at a 90-degree angle. You can't put a detector in front of it and measure the light. Also, the ferrule is recessed inside this connector here, so getting a detector in here to measure light directly is very difficult. So what's suggested is to use a large core receive cord and then treat this like a standard MPO type testing. So this large core receive cord or receive cable is an EBO to MPO assembly built from 62.5 micron fiber. It serves to couple light from the EBO assembly directly to the OPM. So you're going to connect up the EBO to MTP assembly to your optical power meter, and then effectively everything in this gray box is your power meter. It just extends the power meter functionality to the EBO connector. Now, to look at the equipment cabling setup, we suggest using an equipment cord that is a fan out to MPO type connector, and then use a launch cord that is an MPO to EBO system. Also use a receive cord, leave your receive cord connected to the optical power meter. So for the insertion loss reference, we're going to connect the EBO reference cord directly to the large core receive fiber. And again, this is a zero loss connection here, so it's effectively like you're connecting your EBO directly to the power meter. Now for the RL reference, the system's going to scan for an open end of the cable. In this case, because the EBO, open EBOs have very low return loss, we're going to connect a short EBO to MTP PC assembly for the RL reference and calibration verification to 0 to a 14.7 dB correction. Once the return loss reference is done, we're going to remove this short EBO to MTP stub. Now, to measure the loss of the EBO connector, we're going to make the assembly between the reference connector and the receive cable connector, and we'll measure insertion loss and return loss at this connection. Remember, this connection here is a very low, almost zero loss connection here, so we're getting insertion loss of A and return loss of A here. To measure side B, we're simply just going to flip the cable and measure insertion loss and return loss of side B. Now, what to expect when we're testing expanded beam assemblies. To reference return loss, use a short EBO to MTP flat connector to zero the reflection to 14.7 dB. For the 3M EBO connector, pay attention to potential dust contamination on the large core receive cable. So daily usage of this cable will lead to potential dust buildup. To clean, use compressed air to blow away the dust. And remember, for some of these EBO assemblies, measure loss at the quote unquote right location. So this depends on the connector type. So contact your vendor to find out which end of the cable you need to measure return loss on. I'll now pass the webinar off to Paul to present some of the benefits of the new EBO connector. Thank you.
Okay, thanks. I'll spend a few minutes to briefly review the 3M expanded beam optical interconnect. So as Chris mentioned in the early parts of the talk, traditional multi-fiber connectivity is usually based on physical contact connections. And in a nice pristine environment, those connections work really well. However, in operations, there are some difficulties that are encountered, and contamination and dust being big issues. And so these issues with connectors are often implicated in the top causes for network failures. So this has led to, in practice, the incorporation of inspection and cleaning into the current work practices to really mitigate some of these issues. And while effective, these inspection and cleaning practices do introduce time and resources to finish these works. And so this time can slow network commissioning, and use of physical contact connectors can also cause some damage, as Chris alluded to, when contamination is present on the interface and it's not clean. So it was against this kind of backdrop of some problems with physical contact multi-fiber connectors that we were led to develop a new solution. And we call this new solution the expanded beam optical interconnect. And on this page, we kind of highlight some of the opportunities and challenges that were driving our development work. So foremost, we wanted this to work with both single mode and multi-mode connectivity. Single mode performance is generally more demanding because of the accuracies required. And so that was foremost in our development effort, is to realize good single mode performance. Of course, the advantage of an expanded beam connector is that it's much less sensitive to dust. And so that would address the problem of the cleaning and inspection that we've been talking about. At the same time, we want to have very good insertion loss and return loss performance, and not to sacrifice any performance that you might get from a multi-fiber connector today, and that this performance be stable under multiple mating cycles. And lastly, we were focused on developing a connector design that would utilize this expanded beam ferrule in a way that could be scalable. And to that end, the solution that we have has low ferrule mating forces. And so this helps you to develop connectors that have even very high fiber counts. We won't have a chance to cover that today, but that is one advantage. So you see on the right-hand side of the screen, a photograph of the connector in sort of a patch panel situation, and you see in the foreground the connector with the ferrule in the tip there. And it's this expanded beam ferrule that's really the heart of the technology, and I'll describe that on the next slide. So this slide describes schematically the 3M expanded beam optical ferrule technology. If you look on the right-hand side, you see a picture of a ferrule in yellow, and you see these blue bars coming over from the left, and these represent 12 individual fibers. So this is a 12-fiber ferrule, and it's this ferrule that's going to do the beam expansion. You can see on the right-hand side a photograph of the ferrule. It's fairly small. It's about 5 millimeters by 7 millimeters size. Now, if you were to follow the light path through any one fiber and through the ferrule, you would see something that looks like the schematic on the left-hand side. So you have the blue input fiber. The light will diverge from the fiber and then hit a facet on the ferrule. The function of this facet is to serve as a total internal reflector, where it will bend the light 90 degrees and also collimate it in its expanded state. Then that beam will exit the ferrule. At the exit point, there's an anti-reflection coating to minimize loss and back reflection. And then there's an identical ferrule that will receive that expanded beam and then focus it back into the receiving fiber. So that happens for each of the 12 fibers. And so some of the benefits of this geometry is that having the grooves here to receive the fibers rather than holes makes it adaptable to automation. The ferrule itself is ready to go. There's no polishing of the ferrule or of the fiber. And all of the critical alignment features for alignment of one ferrule to another are embedded in the geometry of the ferrule. So there's no external guide pins, for example, to help maintain critical alignment features. And so this helps with the performance and durability of the connection. On the next slide, you see some examples of the single mode performance. In this case, on the left-hand side, you see the single mode insertion loss at 1310 across each of the 12 fiber channels. The loss is around 0.4 dB here, and our current specification is 0.7 dB maximum. Similarly, on the right-hand side, you see return loss, again, for each of the 12 channels in this 12 fiber connector. Loss generally above 60 dB with a spec limit better than 55 dB. So one of the advantages of expanded beam is to be much less sensitive to dust, and also to have different methods of cleaning when you have a non-contact connector. And so we did employ some tests where we subjected connectors to a dust chamber loaded with Arizona road dust and blow that around. And then we can deposit dust on the connector to raise its insertion loss from, say, an initial value of 0.4, 0.5 dB up to around 2 dB after the dusting. And then after the dusting occurs, you can use compressed air to blow off the dust on the ferrule, and then you can remate and measure the insertion loss again. And in this example, the insertion loss was returned back to its original value. And so this shows the effectiveness of compressed air cleaning, as well as the benefit of an expanded beam nature being much less sensitive to dust. Another important property of the connection is to have good performance under a number of mating cycles. And this particular slide shows some performance from 1,000 mates of a single mode connector. On the left-hand side, you see performance for insertion loss, specifically the change in insertion loss from the initial mate across each out to 1,000 mates. And you can see for each of the 12 channels, the variation is fairly small and below 0.1 dB. Similarly, on the right-hand side, you can see a graph for the change in return loss from its initial value through the 1,000 mates. And again, very small change here, generally less than a dB for most of the channels here. And all of this testing here was completed without any cleaning, compressed air or otherwise for this connection. So this demonstrates a very stable remating performance for the insertion loss and return loss. So in terms of specifications, our target specifications are both in the single mode and multi-mode regime. Today we only had time to focus on the single mode, but we've also been in development with multi-mode connectors. To reiterate, on the single mode side at 1310 nanometers, our insertion loss spec is to be less than 0.7 dB and return loss greater than 55 dB. On the multi-mode side at 850 nanometers, insertion loss is less than 0.3 dB and return loss greater than 25 dB. And these connectors today are designed for controlled environment operation where the temperature excursions are in the range of -10 to +60. So with that, I'll have just a quick summary of our expanded beam technology. Today, we've mostly focused on explaining the expanded beam ferrule and its use in a 12-fiber single mode connector. As I mentioned earlier, this can also be used in multi-mode connectors. We didn't have time to touch on the expandability and scalability of the technology, but it's designed to enable that scalability. We've demonstrated connectors up to 288 fibers by simply stacking 12 fiber ferrules in an appropriate way. And you can see on the right-hand side an example of a 288 fiber connector employing several different ferrules. And with that, I'll conclude my brief introduction into the EBO connector, and then we'll turn it open to questions for both Chris and myself about the topics covered in this webinar.
Okay, so I see there's a few questions here. I think I'm going to scanning them here right now. Sorry. I have one question. It's asking about the D-shuffle method. And it says, with the D-shuffle method, how do you validate polarity with a large area detector? With the D-shuffle method, what you're effectively doing is you're allowing the D-shuffle itself to validate the polarity. So if you construct the D-shuffle properly, when it D-shuffles your shuffle, as long as you're getting power out of your D-shuffle assembly, it's telling you that your shuffle assembly is correct. However, it doesn't give you a specific mapping of your shuffle. So if something is wrong, you wouldn't be able to tell where it's wrong. You would just know roughly which input port fiber was incorrect, so you could go back and troubleshoot it that way. But for strictly just checking that the polarity is correct, the D-shuffle method will do that. If the polarity is incorrect, then your D-shuffle, your measurements aren't going to be correct using the D-shuffle. me see here. Another question here was, does swapping the OPM adapters during the hybrid core test affect the reference? So it might affect it a little bit. However, if the optical power meter adapters are designed to be compatible with each other, they shouldn't. So, you know, if you were using adapters from maybe 2 different manufacturers or adapters intended for 2 different applications, then it potentially does affect the reference. But if you're using them from the same manufacturer and for the same application, or they were designed for the same application, then it will not affect the reference.
Hi, Chris. There was a question related to the EBO, so maybe I can answer one of those while you look at some of the other questions. So the question was related to do the EBO connectors have same performance at, say, 1310 and 1550 when using 9-micron fiber? The performance is similar at 1550. The insertion loss is about 0.1, 0.15 dB greater due to some wavelength variation in AR coating or materials, but otherwise similar behavior, and return loss is also similar.
One question here says, with the large core method, does the zero loss contribution apply to both IL and RL? It does not. So the zero loss contribution only applies to the insertion loss measurement. For return loss, if you're mating the back end of your DUT to a large core receive cable, there is return loss at that connection. However, if you're using a pulse-based measurement system, you won't measure that return loss as long as it's far enough away from the front end of the DUT. If you are measuring with a CW type return loss system, then that rear end connection will affect the return loss measurement.
So there's a question here regarding expanded beam. I think it may be directed at something I covered on the meet remating loss. So yeah, what I showed was the change in insertion loss. So the change was very small. It was less than 0.1 dB across the one mating, the 1,000 remates. And so that change is relative to a baseline of about 0.4 dB.
I have one here that asks, what large core receive cable would you recommend for a 62.5 micron DUT? So I would suggest using a 100-140 micron receive cable. The 100-140 fiber is, obviously has a larger core, but it also has a larger NA. The 62.5 micron fiber has a 0.275 NA, and a 100-140 graded index typically has a 0.29 NA. So if you're ordering such a fiber, you do need to make sure that you specify that it's a graded index 0.29 NA. There are 100-140 fibers out there that have different NAs. Let's see here. So I have one here. It's asking about the multi-mode receive jumper. It says on the multi-mode receive jumper, are you using bend insensitive fiber or non-bend insensitive fiber? So in these setups, because we're talking about using a large core receive fiber, most of these, it doesn't really matter whether you're using bend insensitive or non-bend insensitive, as long as the fiber is larger and has a larger NA. However, you know, if you want to get a total link loss and you want to use a receive cord to get a total link loss, I would suggest using non-bend insensitive fiber, because non-bend insensitive fiber will weed out the leaky modes to give you a somewhat of a real insertion loss measurement.
There was another question related to the EBO ferrule and if there were single channel versions. Today there's not. What we have today is the 12 channel version.
I think they also asked, how do you keep the TIR mirror surface clean?
Yes, that not shown in the schematic that I presented, but we have a film that covers the TIR surface, or that portion of the ferrule geometry, to protect it. And so that's how we keep it clean.
Okay.
I did have one question for you, Chris, whether there were any substantial differences between a large area detector or an integrating sphere in terms of any of the techniques that you were speaking of.
There are. So a large area detector, you're measuring light directly on the detector. So you're directly incident on it. On an integrating sphere, integrating spheres do really well with incoherent light. However, when you have coherent light, or light from a laser coming in, you can get kind of hot spots on the detector. So it's possible to slightly incorrectly measure power with an integrating sphere. However, the larger the integrating sphere, the more it integrates the light. So there are slight differences, but if the integrating sphere is designed correctly, then it mimics a large area detector very well. I have one question here. It says, why a mismatch in the NA will not create an IL on the receive cable side? So in using a large core receive cable, like for example, if you take a 50 micron fiber and you made it into a 62.5 micron fiber, the 62.5 micron fiber has a larger NA, which means it can accept light from larger incoming angles. So the 50 micron fiber has a 0.2 NA, which means it's the light exiting it has a shallower angle than what the 62.5 micron can accept. So if you just think about the acceptance cone on a 62.5 micron fiber being much larger than on a 50 micron fiber, and that's what leads to the loss. If you had an NA larger, if the 50 micron fiber had a larger NA, the large NA light would actually create loss on the 62.5 micron fiber, even though the 62.5 micron fiber has a larger core size. You just need to match that the NA and the core size are larger than the cable that you're testing. There's one question says, is there some multi-fiber MPO MTP reference existing on the market, and is it standardized? This says the same question for expanded beam connectors. So for MPO and MTP, there are no standards developed for a reference type connector. They are in the process of being developed, and they've also been in the process for probably the last 4 or 5 years, just very slow moving. There are suggested geometry standards and insertion loss and return loss requirements that can be given for guidance. If you would like some of that guidance, you feel free to contact Octotest, and we can share with you some of the requirements and standards that we use for our MPO and MTP reference cords. There's one question here about it asked also if there were reference connector requirements or standards for the EBO connector. Paul, do you guys have any requirements for those?
We do. I guess I guess maybe request someone contact me privately to discuss that.
Okay. It says, for RL measuring, same question. What is a reference connector? Is it a connector that RL is known? Because when you measure RL on an EBO connection, you measure the entire RL. Yeah, so I think that's probably dependent on the manufacturer. So I'm sure the EVO connector has a different requirement for the reference connector. You know, other expanded beams probably have different requirements for the reference connector. What I showed in my presentation was that, you know, the reference connector itself induces most of the return loss when you're coming in from the source side of that reference connector. I don't think that's the same necessarily for the EVO connector, but for, you know, for expanded beam assemblies that use kind of ball lenses, I think that's kind of the case. So I'm not sure. You probably have to contact the manufacturer of the connector to find out what those requirements are. I think that's it for all that we have for all the questions. I think I already answered these guys that are left over.
Well, fantastic. Well, thank you guys so much for joining today. Thank you, Chris and Paul, for presenting. Just a reminder to everyone, the recording for today's webinar will be posted online, hopefully before the end of the week, hopefully in the next day. And I also dropped in the chat box the support@optatest.com email address. If you reference the webinar Q&A in the subject line, Chris and his team can definitely reach back out to you guys if there are any questions that were not answered, or if there are any more questions that you might have. So thank you guys again for participating and attending, and we'll see you guys at the next one.
Thank you.
Thank you.
Take care. Bye.